Excellent. Would somebody mind unmuting and just saying hi real quick so I make sure that I can hear you through my iPad?
Hi.
Perfect, thank you. Okay, and we're recording, so that should be all good. Got a couple minutes. Your exams are here at the front. If you didn't grab them, make sure that you leave the folder. For the people who took the exam online, I haven't finished grading those yet. They take a lot more time to grade online, but I'm hoping to finish those by the end of the day. So if you took the exam in person, I've got your test here, and if you took it online, hopefully by the end of the day. For the people that are online, I'm going to try to keep an eye on the chat. If you ask a question in the chat, I don't see it, feel free to just unmute yourself and get my attention. Okay, let me start off with a couple of announcements. We'll start with exam 1, since you hopefully just picked that up, and if not, they're here in the folders. So on your exam 1, let me reiterate what I said before. If you took it in class, it's here in the front. If you took it online, I'll have it for you hopefully by this afternoon or this evening. It had 6 questions, and so remember that every question in our course is graded with one of 4 letters, E, M, P, or I. You should think of E and M as basically passing. E is either perfect or one tiny little mistake on a big problem. M is mostly correct, but you had a couple errors. P means that you had a substantial part of it wrong, and I means that you basically left it blank. I don't think there were any I's on the exams that I've looked at so far. So on the front, you see 6 letters corresponding to your grades for the 6 different problems, and you see a revision date. So just like anything else, the revisions are due a week from today by the time class starts. That would be noon on Monday. Exam questions are the most expensive to revise. It costs 2 tokens per exam question. You should have plenty of tokens to revise at least a couple. Probably you don't have enough tokens to revise all 6, but I don't think anybody's in a situation where they need to do that. You want to look at the grade matrix. Remember, we pulled that up on our website a couple of classes ago, and I think after we got quiz 1 grades back, and we looked at how to check off your grade. So go back and do that with your exam. You should be doing that at home every time you get a grade back. Every E you get, you check off a box in the row that's just for E's, and every E or M, you check off a box in the row for E's and M's. So take a look at the number of boxes there and take a look at what you got and try to figure out what you want to revise. My general advice for exams would be it's not worth it to revise an M up to an E. That's probably not worth the 2 tokens. The only exception to that would be if by the end of the course you've got tons and tons of M's and not enough E's for the grade you want. That's a little bit of a different situation. At this point, I would only recommend revising P's so that you hopefully bring that up to an E or an M. And if you got just like 1 P and the rest are good grades, you might decide, well, I'm going to save my tokens, and that's fine. If you got a bunch of P's, you might want to do some revisions. So when in doubt, definitely email me or talk to me during office hours, and I'm more than happy to help you figure out how you're doing, how your grade's looking, and help you figure out what you want to revise. So that's exam 1. Any questions? Okay, our next announcement, I just want to remind you, homework 2 is due on Wednesday. You've had that for, I think, 12 days now, so hopefully you've made some progress there. That covers 1.3 and 1.4 and most of 1.5, and we finished about half of 1.5. We're going to finish it up today. So by the end of today, for sure, you'll have everything that you need to know for homework 2. Although before today, you have everything up to, I think, maybe 1, maybe 2 problems. So that's due on Wednesday by the time you get here in class. For the people who are joining us online, that's due on D2L. I'll make sure to set up a folder for submission. Oh, no, wait. Sorry, I forgot. We're all turning in homework online. Right, so you guys are doing homework in LaTeX, turning that in online on D2L. I forget if there's a folder there now, but I'll make sure there is one if there isn't already. Okay, sorry for the confusion. Kind of hard to keep everything straight here. Any questions about homework? Yeah. So the question is, when can you submit revisions for homework 1? Revisions are always due a week after you get the grade back. So I forget which day I returned homework 1, but if you look on it, if you look at your feedback, there's RD and then a date, and that's your revision deadline for an assignment. So I don't remember if a week has passed already, but if a week has passed, then it's too late. You can turn in revisions as soon as you get it back, as long as I've remembered to make the revision folder on D2L. If you have revisions to submit and you don't see the folder, email me so I can make sure to create it. Any other questions? Okay, and the last announcement, I just want to remind you, in case you've forgotten, that I have normal office hours. They haven't changed or anything, but I just wanted to remind you of the times. My office hours are Mondays, so today, 2:30 to 3:30 p.m. on Teams. Tuesdays, 1 to 2, also on Teams. And Friday, this is really an office hour for my calculus students, but it's pretty common that there's nobody there from my calculus class. So if you have a question, you're welcome to come on Friday, and I'll probably have time to answer it then as well. So these are my 3 office hours. I've seen some of you in office hours, but definitely not all of you. So if you're stuck on understanding something in lecture, stuck on a homework, stuck on doing a revision, you can ask about anything in office hours. You can even ask about exam revision, so totally fine. Okay, before we jump back into 1.5, are there any questions about anything going on in the course? Okay, so we got a couple pages into 1.5 last time. 1.5 is our section on implications. And we saw implications appear in one question on the exam, the question where you had to do a truth table. And one of the last things we talked about is how you can rephrase an implication in terms of symbols we've already learned. So let me remind you of a couple things. We write our implications like this, and we read this out loud as P implies Q. Or another way to phrase that, if P is true, then Q is true.
We can't see the screen from online.
Oh, you can't see what I'm writing?
Mm-mm.
Can anybody else chime in?
Yep, from my end, I'm able to see what you're writing. I've got P implies Q, and if P is true, then Q is true up on my screen now.
Okay, so at least one person can see it. If you can't see it, maybe try leaving the meeting and rejoining. Or you may have to look among all the windows at the bottom and choose one to pin. So give that a shot, and if it's still not working for you in a minute, let me know, okay? All right. Hopefully that fixes that. Okay. So if P is true, then Q is true. And we explored the what this means. And we said that P implies Q is false only when P is true and Q is false. That's the only time P implies Q is true. So if the thing we're assuming is true, but the conclusion is false, that's bad. Every other scenario is good. If you have a true statement implying a true statement, that's good, that's true. And then the other one, which was a little bit weirder, is that if the thing you're assuming is false, if P is false, then the whole implication is true regardless of what Q is. One way to think about this is an implication says, if P is true, then Q is true. And then kind of implicitly, it says, if P is false, I don't care about Q. So the truth table for an implication looks like this. So we've got true, true, false, false in the P column, true, false in the Q column. And then our values for P implies Q are true, that's a true implies true. And then this second row, that's the only bad situation. P is true, but Q is false. So that one's false. And then in the last two rows, P is false. And we said if P is false, I don't care about Q. So it's true in these last two rows. Okay, the person who is having trouble, have you had any luck?
No, I haven't.
Did you try leaving the call and rejoining?
Yes.
Okay, let me try. I will stop sharing the screen and then start again. And let me see if that helps here.
I honestly think it's just something on my end though, because I'm texting other people in the class and they can see everything.
Okay, I'll just try this just in case. Okay, so the screen should be.
That worked.
That worked, perfect. Okay.
Yeah, thank you.
Thanks for telling me that you had a technical error instead of just not saying anything for 50 minutes. Okay, so hopefully we're good now. So we've got our truth table here. And the last thing I said last class is that P implies Q can be written in terms of symbols we already seen. It's logically equivalent to saying not P or Q. And the reason this is the case, I mean, number one, you could just draw the truth table for both sides and see that they're the same, although that doesn't give you any intuition. The reason this is the same is that this thing over here says, if P is false, then my whole thing is true. Okay, good. But on the other hand, if P is true, this is going to be false, so that doesn't make my or statement true. But if P is true and then Q is true, that's going to make it true. So this says P implies Q means either P is false or Q is true. And that's kind of where we left it last time. Any questions? Okay, so we had a bunch of questions at the end of last time on, I guess on Wednesday, saying like, well, why do we want our implication to be true if the hypothesis is false? Why are we setting it up that way? And I want to do an example now that will hopefully kind of clear that up. So this is an example about drinking laws. And this is an example that's in the book, and I think it's a really illustrative example for understanding implications. So let me remind you of the drinking laws, just in case I have to. The drinking laws say you must be 21 to drink. An interesting trivia tidbit that most people don't know is that there's no federal law that makes the drinking age 21. There are 50 state laws individually that make the drinking age 21. And the federal government told the states, in I think the 50s, they said, hey, every state, if you don't make the drinking age 21 instead of 18, we're not going to give you any money to build your highways. And every state decided they wanted that highway money, so they made the drinking age 21 to get the highway money. So there's no federal law, just a bunch of state laws. Okay, so I want to take this law, you must be 21 to drink, and I want to phrase that like an implication. And there's a lot of wrong ways to do it that sound right at first. We're going to try to be really careful to make sure that we get it right. So to follow the law, we're going to try to write an implication. So we're going to say if something, then something. Our goal here is to create an implication that will perfectly capture whether or not you're following the law. So if you're breaking the law, we want our implication to be false. If you're following the law, we want our implication to be true. So I want to give you guys maybe 30 seconds or a minute to think about this. This is a good exercise. I'm not looking for math symbols. I'm just looking for English to fill in the blanks. I want you to try to devise an implication that's true exactly when you're following the law and false exactly when you're breaking it. So take a minute, write it down, and then once you write it down, read it to yourself and think about whether or not that works. Okay. So does anybody want to try to volunteer and fill in the blanks? You're welcome to speak up or use the chat on Teams if you'd like to as well.
I'd like to give it a shot.
Yeah.
Whoops.
Oh, yeah. You might need to lower your speakers a little. Okay.
But,
what do you think?
So I'm thinking if you are allowed to drink, then you are at least 21.
Okay. So let me write what we see here. If you're allowed to drink, then you must be 21. Okay, so let's think about this. We want this statement to be true if we're following the law and false if we're breaking the law. So there are several situations in which you could be following the law. And I want to just rephrase this first part just a little bit differently. I think it just makes a little more sense. So let me just slightly rephrase this and say, if you are drinking, then you are greater than or equal to 21 years old. Okay, so first off, I'm adding this greater than or equal to because, of course, if you're 22, you're still allowed to drink. And I'm also just rephrasing this to be in the present tense because it's going to make a little more sense when we go further into the example in a minute. Okay, so does this make sense? If you are drinking, then you are at least 21. Well, a couple different things could be true. What if I am drinking, but I'm not 21? So if I'm drinking and I'm 20 years old, and how do these evaluate? Well, let's just write this here. If I'm drinking and 20 years old, then this first part here, that's true. I'm drinking, that's what I said. And I'm at least 21 years old is false. So in this situation, we have a true implies false implication. And if we look back up at our truth table, that was exactly the case that we said was bad. So that gives us a false implication. Okay, so that's part of what we wanted. I'm breaking the law if I'm drinking and I'm 20, and I get a false implication. Good. There are a couple other cases where I could be following the law. One is that I'm drinking and I'm 21 years old. So that's another case. Drinking and 21 years old. In this case, I'm following the law, and so I want a true implication. And what we end up getting is a true, because I'm drinking, implies true, because I'm at least 21. So this is a true implies true, which is true. Okay, one more example before we go into the second half of this example. What if I'm not drinking? And I am, let's say, 30 years old. If I'm not drinking and I'm 30, am I following the law? Yes. And does that make sense with what we have here? We've got a false, because I'm not drinking, implies true, because I'm at least 21. And if we look at our truth table, even though it seems a little weird at first, that is a true implication. So I'm following the law because I'm not drinking at all. The law says if you're drinking, you have to be 21. And implicitly, the law says if you're not drinking, I don't care how old you are. So this is an example. We've got a false implies true. The hypothesis is false. Therefore, I don't care about the conclusion. And that gives me a true implication. Any questions? Okay, so here's the second half of this example. Suppose you've got 4 people. You've got Al, Betty, Cindy, and Dan. And suppose that they write their age on one side of a card and the beverage they're drinking on the other. Okay, so this is the situation. All 4 of them have an index card. On one side, it says how old they are. On the other side, it says what they're drinking. And then they put them on the table, some of them facing in different directions, and they look like this. So Al's card says 19. So you see that Al is 19 years old, but you don't see his beverage because that's on the other side. Betty's card says Coke. So you know what she's drinking, but not her age. Cindy's side says beer. And Dan's side says 25. So that's our setup. Now, a cop walks in and wants to figure out who is breaking the law. The question is, whose cards does she have to flip over to figure out who's breaking the law? So I'll give you a chance to catch up and write all this down, and then we'll think about this. So let's remember what breaking the law means in terms of our symbols. Well, following the law is P implies Q based on what we wrote above. So P is drinking. Really, we mean drinking alcohol. And Q is greater than or equal to 21 years old. Now I'm doing something that I tell you guys not to do. I made my statements not full sentences. So do as I say, not as I do. I just needed a little bit more room here. If you were writing this out, it should really say P is you are drinking alcohol, and Q is you are at least 21 years old. You need nouns and verbs in your statements because they have to be full sentences. So following the law means P implies Q. The cop wants to know who's breaking the law. Breaking the law means the negation of following the law. So that's the negation of P implies Q. And I want to write this out in terms of the other way to write implications. So we said that implications could be written as not P or Q. And so let's negate this. So we have to remember how to negate. We have a law that tells us what to do. This is De Morgan's law. It says if you want to negate an and, you take the negation, you apply it to both of the inside parts, and then you do what? What else do I have to do for De Morgan's law? Can you say it a little louder? Yeah, you have to change the and to an or. De Morgan's law says you take the negation, you apply it to both parts, and then if you have an or in the middle, you change it to an and if you have an and in the middle, you change it to an or. So let's do that. We get not P, just gives us P. The or becomes an and the Q gets its negation. Okay, so what does this say? It says you're breaking the law if you are drinking and you are less than 21 years old. So we could obviously figure that out in English. I mean, we just know this is true, but now we've gone through the symbols and discovered the same thing. So the question is, whose cards does the cop have to flip over to see if they're breaking the law? So let's go back up here and look at the cards. The cop walks up to Al to start with. Does the cop need to flip over Al's card? See, lots of nodding. How come? When we put it into words, we all kind of see that it's true. Yeah. Yeah, he's less than 21, and therefore, the cop needs to know what he's drinking. So, for Al, we know Al is 19. That means, in terms of the potential for breaking the law, we know that not Q is true. We know that Q is false. Q is false, which means not Q is true. And so we don't know the answer yet. If not Q was false, as we'll see in another example in a second, then we don't need to know P because we've got one of the two parts of an and being false. And so if one of them is false, we don't need to see the other one. But we see that not Q is true, and therefore we have to check P. So yes, Al's card has to be flipped. Because not Q is true, and we have to figure out P to know the answer. Okay, let's move on next to Betty's card. What we know about Betty is that she's drinking Coke, but we don't know her age. Does the cop need to flip over Betty's card? Yeah, I see lots of people shaking their head no. And the reason is Betty's not drinking alcohol, so we don't care, or the cop doesn't care, how old Betty is. So putting that in terms of our symbols, Betty's not drinking alcohol, so that means P is false. And so breaking the law is this symbolic statement here. If P is false, it doesn't matter what Q is. Putting that another way, if we look up at our implication, if P is false, we don't care what Q is. This is part of how we're defining that truth table for an implication. P is false. That's going to make the implication true no matter what. And then we're negating it. So that's false. So then Betty's definitely not breaking the law regardless of the value of Q. So no flip. Any questions on that one? Okay, let's go up to Cindy now. Cindy's card says beer on one side, but we don't know her age. Does the cop have to flip over Cindy's card? Yeah. So Cindy is drinking alcohol, so the cop needs to figure out how old she is. So Cindy is drinking. That means, in terms of our statements, so Cindy is drinking. That means P is true. So in terms of whether Cindy is breaking the law, the first half of this and statement is true. And that means we still need to see the second half to know if the whole thing is true. If P was false, like in Betty's case, the whole and is false no matter what. But in Cindy's case, it's true, so we're going to have to check the other side to figure out whether or not she's breaking the law. So Cindy's card has to be flipped. And then lastly, we've got Dan. Dan's card says 25. So we don't know what Dan is drinking, but we know Dan is 25 years old. Does the cop have to flip over Dan's card? The cop sees that Dan is 25, but does not see what Dan is drinking. Does the cop need to know what Dan is drinking? I think I see some shaking head, so the answer is no. The answer is no flip. Oh, sorry, page keeps running away from me. No flip. And the reason is, if we look one more time at our statements, which one of these two quantities do we know based on Dan's card saying 25? Do we know P or do we know Q? You can just shout it out. We know Q, and do we know whether it's true or false? I think I heard true. If Dan's 25 years old, that means we know from the one side of the card that Q is true. We know Q is true. And if we look one more time at our statement for breaking the law, if Q is true, that means not Q is false. So we've got something and false. That means it doesn't matter what P is. The whole thing is going to be false because one half of it is false. So we don't need to bother flipping the card over to see the other side to know if Dan is breaking the law. Okay, so this example hopefully illustrates, and you might have to go back and think about it again or look at it in the book, illustrates why we want an implication to be true in the case where P is false. If the thing that you're assuming is false, we don't care what the conclusion is because our claim doesn't say anything. We're saying if P is true, then Q is true, and implicitly, if P is false, then we don't care. Any questions? We had an example of that last class. It was something like, if the moon is made of cheese, then I am 6 feet tall, or something like that. And that was a false implies false. Neither of those things are true as far as we know. And that's a true implication, which seems really weird. That's one of the ways that the phrase something implies something seems to violate the way we say that in English. Here's another example. Let's say if Jay's hair is brown, then today is Monday. So this is certainly an implication. It sounds weird in English, especially if you phrase it the other way. Jay's hair is brown implies today is Monday. That definitely doesn't seem like it should be true in English, because in English, when we say implies, we're kind of also saying there's a cause and effect. And there's obviously no cause and effect between my hair color and the day of the week. But in math, this is true, and this is true, and therefore we have a true implies true implication, which is true. So the moral of the story here is you have to ignore the cause and effect connotation that English has. So even though the first thing definitely does not cause the second thing, you phrase it like an implication, then it's a true implication. Any questions about that? Okay, and just to drive the point home, let's slightly change this example. Just copy and paste it here. Let's take the same example, and let's change brown to blue. Oh, I forgot the word hair. That's an important word, isn't it? Okay, so this is a false implies true. My hair is not blue, but today is Monday. Does that make this a true or a false implication? Yeah. Jack says false. I'm a little suspicious of that answer. Anybody want to take another shot? I guess it's pretty clear what the answer is now. Yeah. Yeah, it's true. Although, thank you for answering. Remember, I love wrong answers. This is true. It's hard to remember which way this goes. If you have a false implies true, and you look all the way back up at our truth table, that's a true implication. If you have a true implies false, that's a false implication. This is, I think, a prime example of something that you could memorize, although that's a lot of work trying to memorize something like this. You should instead think about what it means. An implication means if P is true, then Q is true. It doesn't make any claims about what happens when P is false. So false implies true does not invalidate anything. True implies false is the problem. Okay, so this is a false implies true, which makes it a true implication, which is weird because once again, we're using English statements. There's no cause and effect there. It's ridiculous to say Jay's hair is blue. This certainly doesn't imply that, but it's still a true implication in math. So I just wanted to make that point a couple of extra times. Now, I've used these words a bunch of times. I should actually define them. If I have P implies Q, we call P the hypothesis, and we call Q the conclusion. That's probably something I should have defined at the beginning, but we've said it a bunch of times. So an implication is really saying, if my hypothesis is true, then my conclusion must be true. And then the implicit part says, if my hypothesis is false, then I don't care about the conclusion. It could be true or false. Doesn't matter to me. Okay, one other thing that I want to point out. Let me write an example implication. So let's say if you get all the exam questions right, then you pass the class. Which part of this is the hypothesis? I'd like to hear from somebody I haven't heard from yet today. If anybody's brave enough to answer in person or online, you can use the chat or your voice. Yeah. Sorry, can you say it again? Yeah. The hypothesis is the part attached to the if. You get all the exam questions right. So this is the hypothesis. And that makes this other part, you pass the class, the conclusion. Now, you don't want to include the word if or the word then inside of the hypothesis or conclusion. They're kind of just the structure of the implication. So the hypothesis is you get all the exam questions right. The conclusion is you pass the class. Now, let me write the exact same implication, but in a different way that is kind of confusing. But you'll see this a lot in the book, and you'll see this a lot in people making statements in real life. So here's another way to phrase the exact same thing. You pass the class if you get all the exam questions right. This is how a lot of implications are phrased in math or in English. You might say, you win $1 million if you win the lottery. This is not a different implication. It's just phrased a different way. The key is to look at what the if is attached to. The if is still attached to, you get all the exam questions right. So this is still the hypothesis. The hypothesis is whatever's attached to the if. Now, another thing that makes this a little tricky is that the word then doesn't appear. And that's because in English, you would never say, then you pass the class if you get all the exam questions right. That's just implied in English. So this now is the conclusion. So this is the same implication. Even if it's out of order, the P is still, you get all the exam questions right, and the Q is still, you pass the class. Any questions? Okay, we are doing pretty good on time. I think we'll finish 1.5. Let me show you some examples now where you use implications with quantifiers. Now we're going to bring in quantifiers. Almost all of the time that implications are useful in math, it's when there's a quantifier. And you saw examples of quantifiers on the exam, although you didn't see ones with implications, I don't think. But you might say something like, for all natural numbers n, if n is even, then n squared is even. That uses a quantifier because we're saying something. We're saying if it's even, then when you square it, you still get something even. But we're not saying that for one number, we're saying it for all numbers. So that's where the quantifier comes in. So let me show you an example. For all x in the real numbers, if x squared is greater than 4, then x is greater than 2. This is an implication with a quantifier. The implication itself has one variable, x, and therefore we need one quantifier. Anytime you have a variable, and this should make some sense if you're just trying to convince somebody of a fact. If you say a variable, you have to tell the person where that variable comes from. Are you talking about real numbers, integers, something else? Are you saying it's true for all of them? Are you saying it's true for one of them? You have to make that part clear. So if this is so this is now one big statement. If this is true, we're saying for all real numbers, if I square that number and get something greater than 4, then my original number must have been greater than 2. Is this a true or a false statement? Yeah, go ahead. Yeah, you. Okay, you think it's a false statement, and I'm claiming it's true for all of them. So if you think it's false, then how do you convince me? You give me a counter example. Okay, so what's a good counter example? -3, yeah. So this is false. And if I'm making a statement about for all, then the way that you convince me I'm wrong is you give me one example that fails. And even if lots of other ones work, if you give me one that fails, that means it's not true for all of them. So you said x equals -3, and let's see why that fails. So the hypothesis now is -3 squared is greater than 4. That's 9 is greater than 4. That's true. And then the conclusion says -3 is greater than 2. That's false. So your counter example gives me a true implies false implication, and that's the one case. That means my implication is false. Now, on the other hand, here's a wrong answer that you could have given me when I asked for a counterexample. You could have said, let's say x is -1. So I'm writing a bad answer here. If you had said x is -1, this is not a counterexample. I think you probably understand that intuitively. It does not invalidate my statement. Let's think about what the implication looks like. This says -1 squared is greater than 4. That's 1 is greater than 4. That's false. And the conclusion says -1 is greater than 2. That's also false. So that's a false implies false. Hopefully this kind of makes it clear a little bit more why we want false implies false to be a true implication, because I don't want -1 to be a counterexample, because it's not. We're saying if x squared is greater than 4, if this is true, then this is true. -1 does not invalidate this because the hypothesis fails. It does not invalidate my claim. So it doesn't matter that the conclusion also fails because it fails the hypothesis, so it's totally irrelevant. So it's a false implies false, and we want that to be a true implication. It does not invalidate the implication. Any questions about that? Okay. On the other hand, if I had put this slightly differently, and let's say I form the quantified implication for all x in R, in the real numbers, if x cubed is greater than 8, then x is greater than 2. So this x cubed is greater than 8. That's my hypothesis. And x is greater than 2. That's my conclusion. This is not a false statement. This is now a true statement. You won't be able to come up with a counterexample that makes my implication false. And the reason is, you may remember from pre-calc or whatever, that when you cube a negative number, you get a negative number. When you cube a positive number, you get a positive number. So unlike the squaring case up here, where you could come up with a negative number that when you square it, the negative sign goes away, that won't happen in this one because we're cubing it. So this is a true statement. Any questions about that? Okay, so I've got one more topic here that I think we'll finish, and then we'll be done with 1.5. That means we'll be done with chapter 1, and then next class we'll skip ahead to chapter 3 for a little bit before going back to chapter 2. Okay, let me see. I think I want to skip this. Let me just see what I wrote here. Yeah, okay. So one other thing we want to say. There are some relatives of implications that are important. If we have an original statement, like, for example, P implies Q, and let me write our typical example. If you are in Milwaukee, then you are in Wisconsin. I'm just going to abbreviate it because I'm out of room here. There are 3 important relatives of implications. And this relates to the last question that you have in your homework, I think, or at least one of them. These 3 relatives are called the converse, the inverse, and the contrapositive. We saw when we did this example earlier that if you take the statement P implies Q and you swap their order and make it Q implies P, that you might take a true statement like this is and turn it into a false statement. So this would say, if you are in Wisconsin, then you're in Milwaukee. This is called the converse. When you switch the hypothesis and the conclusion, that's the converse. For this particular example, the statement is true, but the converse is false. So this could make a difference. It's also possible to have a statement be true and the converse also be true. That's possible. Yeah, the main point is that knowing whether the statement is true or false tells you nothing about the converse. The inverse is the relative that you get. Instead of swapping the order, you get the inverse by taking P and Q and making them both negative. So the inverse is not P implies not Q. So this would say, if not in Milwaukee, then not in Wisconsin. If you think about that, that is also a false statement. And lastly, the contrapositive is what you form by doing both of these. You switch the order and you negate them both. That's not Q implies not P. That says if you're not in Wisconsin, then you're not in Milwaukee. And this is true. If you're not in Wisconsin, then you definitely can't be in Milwaukee. So we'll end with this important fact. I'll probably write this as 2 facts. These will be fast, don't worry. Fact 1, an implication or statement and its contrapositive are always logically equivalent. So the statement and the contrapositive are always both true or both false. If one is true, the other is true. If one is false, the other is false. The same is not true for converse and implication. They're not the same as the statement, but they are the same as each other. So that's fact 2. The converse and the inverse are always logically equivalent. So that tells us these 2 facts: the statement and the contrapositive are always the same, and the converse and the inverse are always the same as each other, but there's no relationship from one to the other. It's totally possible to have a true statement and a false converse, or true and true, or false and false, or false and true. Any combination of those is possible. Any questions before we end for the day? Okay, I'll see you guys on Wednesday or earlier in office hours.